The universe may be full of intelligent civilizations right now. So why has nothing ever reached us? Today, we find out exactly why it is physically impossible for any alien civilization, no matter how advanced, to ever reach Earth, and why the cosmos itself was built to keep every civilization permanently, inescapably alone. Before we go any further, if the cosmos keeps you curious, a like and subscribe means the world to this channel. Now let's begin. In 1977, NASA launched a spacecraft called Voyager 1. It has been flying every single second since then. No stops, no slowdowns, no detours. Nearly 50 years of uninterrupted travel through the void. And here is what that half-century of flight has actually accomplished. If the entire journey of our solar system were shrunk down to the length of a standard football field, 100 meters from end zone to end zone, Voyager 1's position today would be roughly 2 footsteps past the starting line. Not 2 yards, not 2 first down markers, 2 footsteps. The nearest star beyond our sun sits at the far end zone 100 meters away. Voyager has covered 2 steps of that journey in 50 years. That is not a metaphor designed to make a point. That is the actual ratio. The spacecraft is traveling at approximately 38,000 miles per hour. That is 22 times faster than a rifle bullet. It has covered roughly 15 billion miles. And it has not yet crossed the distance that light, the fastest thing in the universe, covers in a single day. 1 light day. That is where Voyager sits after half a century of flight in relation to where it needs to go. Here is the paradox that makes this genuinely difficult to sit with. Humanity has achieved things that would have seemed like pure mythology to any civilization a few centuries ago. Astronauts have walked on the moon and returned safely. Telescopes have captured images of a black hole 65 million light-years away, an object so extreme that not even light escapes its gravity. Scientists have decoded the full genetic blueprint of the human body, every 3 billion base pairs of it. These are not small achievements. These represent centuries of accumulated genius, sacrifice, and relentless ambition. And yet, against the distance that light needs 4 years to cross just to reach the nearest star, all of that achievement becomes irrelevant. The moon landing, which required the most complex engineering operation in human history, moved us roughly 240,000 miles from Earth. Alpha Centauri is approximately 25 trillion miles away. The ratio between those two numbers is so large it stops feeling like math and starts feeling like a different category of reality altogether. So the question worth asking is not the one that fills science fiction novels and late-night discussions. Not do aliens exist? The universe contains an estimated 2 trillion galaxies, each holding hundreds of billions of stars, many of those stars hosting planets. The probability that Earth hosts the only intelligent life across all of that is by any reasonable calculation extraordinarily small. That debate is essentially settled. The real question, the one almost nobody talks about seriously, is this. Why does the universe, even if it contains thousands of civilizations, seem structurally designed to ensure none of them ever reach each other? Think about what kind of prison looks like. The conventional image involves walls, bars, locks, guards, physical barriers that keep something contained. The universe builds a different kind of prison, one with no visible walls at all, no bars, no signs telling you that you cannot leave, just distance. Unimaginable, unrelenting physics-enforced distance in every direction. And that distance is more effective than any wall ever built, because walls can be climbed, tunneled through, or destroyed. Distance simply exists, waiting, indifferent, mathematically exact. If a civilization somewhere in the Milky Way is currently moving toward Earth, perhaps they detected something interesting about our sun, perhaps they launched a probe centuries ago, there is essentially no way for us to know. The signals that would tell us someone is coming travel at light speed. The craft itself, if it exists, travels slower than light. By the time any warning arrived, the situation would have already changed in ways we cannot predict. The universe does not send notification alerts. And consider this. If some civilization launched a mission toward Earth 10,000 years ago, traveling at a velocity that represents a serious engineering achievement, by any standard, say 1% of the speed of light, where would that mission be today? The math is straightforward. 1% of light speed covers roughly 1/10 of a light year per year. In 10,000 years, that covers 1,000 light years total. If the civilization is more than 1,000 light years away, their 10,000-year-old mission is still in transit, still traveling, still not here. 10,000 years of continuous flight and still potentially thousands of years from arrival. 10,000 years ago, humans were just beginning to develop agriculture. There was no writing, no cities, no mathematics beyond basic counting. Every civilization that has ever existed on Earth, Mesopotamia, Egypt, Greece, Rome, the Islamic Golden Age, the Renaissance, the Industrial Revolution, the entire arc of recorded human history fits inside the travel time of a mission that launched before any of it began and still has not arrived. That is not a failure of alien technology. That is the architecture of the universe operating exactly as the laws of physics require. The most unsettling thing about all of this is not the scale. Humans are reasonably good at intellectually accepting that the universe is large. The unsettling thing is the implication, the very features of space-time that allow stars to exist, that allow planets to form, that allow chemistry complex enough to produce life. Those same features enforce a quarantine between every civilization that life produces. The universe creates the conditions for minds to appear, and then builds a structure around each mind that makes genuine contact with any other mind effectively impossible. Not difficult, not expensive, not merely challenging in the way that landing on the moon was challenging, effectively impossible in a way that does not yield to more funding, more intelligence, or more time. To understand why the universe locks us in, you first need to understand the scale at which the human brain is being deceived. The human brain is, by most measures, the most sophisticated information processing system ever observed in the natural world. It can learn languages, compose music, derive mathematical proofs, and feel grief for people it has never met. It is genuinely extraordinary. It is also catastrophically unequipped to perceive interstellar distances accurately. And this is not a flaw, it is the entirely predictable result of what the brain was built to do. Evolution does not optimize for cosmic accuracy. It optimizes for survival on a specific surface, under specific gravitational conditions, with specific sensory inputs. The human visual system, the memory system, the spatial reasoning system, all of it was shaped over millions of years by one operational requirement: navigate and survive on a planet with a radius of about 4,000 miles. Judge whether a predator is close enough to be dangerous. Estimate whether a river is narrow enough to cross. Calculate whether a thrown object will reach its target. Every cognitive tool the brain developed was calibrated for distances measured in feet, miles, and at the extreme upper end, maybe a few hundred miles, on a clear day from a high elevation. Nothing in the evolutionary environment of Homo sapiens ever required accurate intuition about distances measured in trillions of miles, so the brain has none. What it has instead is the ability to process large numbers as pure symbols representations that carry no emotional or intuitive weight proportional to their actual magnitude. Consider what happens when someone hears the phrase 1 billion seconds. The brain registers it as a large number. Many seconds. A lot. The word billion triggers a general sense of magnitude more than a million, presumably quite a bit, but no genuine felt sense of the difference. 1 million seconds is 11.5 days. 1 billion seconds is 31 years. The difference between those two numbers is not a bit more. It is the difference between less than 2 weeks and an entire generation of human life. But the brain, without being forced to calculate explicitly, treats them as roughly the same category of large. Both feel like a lot of seconds. The 30-year gap between them invisible to intuition. Now take that limitation and apply it to a night sky. When anyone looks up on a clear evening and sees stars, the brain does something it does. With every visual scene, it constructs a unified spatial model and projects everything onto what is effectively a flat screen. Stars appear to be scattered across a dome at roughly similar distances, some brighter, some dimmer, all part of the same visual field. The brain cannot perceive depth at astronomical scales because there is no sensory information available from which to construct it. So it defaults to its standard model flat uniform nearby-ish. This is not a minor perceptual quirk. It is a fundamental misrepresentation of the actual structure of space. The stars visible in any given patch of sky are not at similar distances. They occupy wildly different positions in three-dimensional space, separated from each other by gaps that can span hundreds of light years. The brain folds all of that depth into 2 dimensions and presents it as a coherent scene. And it does this so seamlessly that most people never notice it is happening. Take one of the most recognizable star patterns visible from the continental United States, Orion. the Hunter prominent in winter skies across the northern hemisphere. The three stars forming Orion's belt, the bright stars at his shoulders and feet, they appear to be a group, neighbors, a cluster of stars that belong together. They do not. Rigel, the bright star at Orion's lower right, sits approximately 860 light-years from Earth. Betelgeuse, the reddish star at the upper left shoulder, is roughly 700 light-years away. Bellatrix, the other shoulder, is about 250 light-years out. These stars are not near each other. They are separated by hundreds of light-years of empty space. They appear as a group only because they happen to fall along similar lines of sight from Earth's specific position in the galaxy, the way three buildings in different cities might appear to be standing next to each other when viewed, from a particular angle through a very long lens. The brain assembles them into Orion because that is what the brain does. It finds patterns, creates groupings, and builds useful models from incomplete information. For almost every purpose in ordinary life, this is an extraordinarily valuable capability. For understanding the actual structure of interstellar space, it produces a picture that is almost entirely wrong. Now here is where this becomes important beyond mere cognitive curiosity. If human brains systematically misrepresent the distances between stars that are already known, measured, and charted, what does that do to intuitions about whether those distances can be crossed? Every casual assumption about alien visitors arriving at Earth rests on a foundation of this perceptual error. The sense that the stars are out there in some navigable way, that the gap between here and Alpha Centauri is like a very long ocean voyage, rather than something categorically different from any journey ever attempted. All of that comes from a brain that flattens three-dimensional space into a dome and assigns no genuine magnitude to numbers like 25 trillion miles. It gets stranger still. If there are civilizations on planets around other stars, and there is no scientific reason to assume there are not, their brains evolved under similar constraints. A mind that developed on a rocky planet, under the gravity of a star navigating a landscape measured in thousands of miles, would face the same perceptual limitations. Their intuitions about interstellar distance would be just as miscalibrated as ours. They would look at the star field around them and see something that felt reachable, approachable, a map with destinations rather than a void with no edges. Which means that the entire genre of science fiction, every story ever written about alien civilizations deciding to cross the stars and visit somewhere else, was imagined by minds that are constitutionally incapable of forming an accurate, intuitive picture of what that crossing actually involves. The stories feel plausible because the brains writing them and reading them share the same built-in misperception. The universe looks traversable from inside a skull, shaped by evolution, for a completely different scale of reality. There is something almost poetic about it, though perhaps ironic is the more accurate word. The same cognitive architecture that allows a mind to look up, recognize patterns in the stars, and begin asking questions about what lies out there, is also the architecture that systematically prevents that mind from understanding how far out there actually is. So what is the actual distance, and how brutal does it become when translated into terms a human mind can genuinely feel? Shrink the sun down to the size of a basketball and place it at the center of Times Square in New York City. At that scale, Earth becomes a peppercorn roughly 2 millimeters across, sitting about 26 meters away, somewhere near the edge of the plaza. That is the entire distance between our planet and its star, compressed into a short walk across a city block. Now find the nearest star beyond our Sunday Alpha Centauri. At that same scale, it is another basketball sitting in Kansas City, Missouri, 2,200 kilometers away from Times Square. That is not a walk, that is not a drive, that is a cross-country journey, and it represents the shortest possible gap between any two stellar systems in our cosmic neighborhood. Two basketballs, 2,200 kilometers apart. And between them, across that entire distance, there is essentially nothing. No gas stations, no waypoints, no landmarks of any kind. Just vacuum so complete that the best laboratory on Earth cannot recreate it, at temperatures hovering a few degrees above absolute zero, in a darkness interrupted only by the faint glow of stars too distant to provide any meaningful light. That is the nearest star, the closest one, the galactic equivalent of the house next door. Alpha Centauri carries the word neighbor in almost every astronomy article ever written about it. The nearest stellar neighbor, the closest star system. These phrases do their job efficiently. They communicate relative proximity within a vast catalogue of objects. but they smuggle in a connotation that the numbers do not support. If the solar system were a house, the sun, the planets, the asteroid belt, the outer reaches of the Oort cloud, all contained within one structure, then Alpha Centauri would be another house, sitting approximately 4,000 kilometers away, not across the street, not across town, not across the state, across an ocean and most of a continent. What astronomers call a neighbor by any human standard of the word is an entirely different landmass, and that is the closest one. The James Webb Space Telescope, which began science operations in 2022 and has continued producing extraordinary results through 2024 and 2025, has done something genuinely remarkable. It has detected and analyzed the atmospheric compositions of planets orbiting stars hundreds of light years from Earth. It has identified water vapor, carbon dioxide, methane signatures, the chemical fingerprints of distant worlds, at distances that would have been completely inaccessible to any previous instrument. This is one of the most significant observational achievements in the history of astronomy, and it illustrates with perfect clarity the distinction that matters most in this entire discussion. Seeing is not arriving. When the James Webb Space Telescope observes a planet 100 light-years away, the light it captures left that planet 100 years ago. The telescope is not looking at what that world looks like today. It is reading a message that was sent before World War II ended, before television existed, before the first commercial jet aircraft flew. The planet itself, whatever is happening on its surface right now, is completely inaccessible to any instrument humanity has ever built or could conceivably build in the near future. The relationship between seeing that planet and reaching it is roughly analogous to spotting a single candle burning on a windowsill in Miami while standing in Seattle. The candle is visible with the right equipment, its light can be detected, its color analyzed, its flicker measured. None of that brings Seattle 1 inch closer to Miami. Detecting light across interstellar distances is a triumph of engineering and physics. Traveling those same distances is an entirely different category of problem, governed by entirely different constraints. The Milky Way contains somewhere between 200 and 400 billion stars. Those stars are distributed across a disk, roughly 100,000 light-years in diameter and a few thousand light-years thick. The solar system sits approximately 26,000 light-years from the galactic center, embedded in a minor spiral feature called the Orion Arm, positioned in what amounts to the quiet suburbs of a vast metropolitan structure. If the Milky Way were a city, it would be a city 100,000 light-years across, and every house in that city would be a star system, each one separated from its neighbors by an average of several light-years of empty space. We do not live downtown. We do not live in a busy district with dense traffic and frequent interaction. We live in a remote corner of the outer suburbs on a quiet street, surrounded by the kind of emptiness that most city dwellers never encounter. A civilization genuinely capable of interstellar travel, one that has solved propulsion, energy, life support navigation across light years, would almost certainly not be sitting in the outer suburbs alongside us. The older a civilization, the more time it has had to develop. The stars that have existed longest, that have had the most time to produce complex chemistry, stable orbits, and the long, slow process of biological evolution, tend to cluster toward the inner regions of the galaxy where star formation has been occurring the longest. A truly advanced civilization by many estimates would statistically be found closer to the galactic center tens of thousands of light-years from where we sit. Not 4 light-years away, not 400, potentially 40,000. And here is the question that follows from that, and it does not resolve comfortably if anyone has ever attempted the crossing, drawn by curiosity, by resources, by whatever motivates, a mind advanced enough to look at 25 trillion miles and decide the journey is worth beginning. What happened to them? The universe keeps no record of failed missions. There is no debris field visible from Earth, no signal of a craft that ran out of power somewhere between stars. No indication of an attempt that simply never completed. The silence is total. Whether that silence means no one has tried, or that everyone who tried did not make it, or that the physics made trying irrational from the beginning, that question does not have an answer yet. Distance is only the first wall. Behind it stands another built from something no civilization can manufacture more of: energy. There is a speed limit posted on every highway in the country. It is enforced by patrol cars, radar guns, and fines. It can be violated. Drivers exceed it every day. The consequences are legal and financial, not physical. A faster car simply breaks the posted number, and the universe does not object. The speed of light is not that kind of limit. It is not a rule imposed by some external authority that a sufficiently clever engineer might find a way around. It is not a ceiling that exists because no one has yet built a fast enough engine. The speed of light is a structural property of space-time itself, the fabric in which all matter, all energy, all information, and all physical processes exist and operate. It is not a constraint placed on the universe. It is part of what the universe is. The most useful way to think about it is this. Imagine the universe as an enormous sheet of rubber. Everything that exists, every particle, every wave, every photon, every atom in every star, exists on or within that sheet. The speed of light is not the speed at which things can move across the rubber. It is the speed that the rubber itself permits anything to move. There is no way to hack this limit, no workaround to engineer, no exception to negotiate. The reason is simple and absolute. You are not something separate from the rubber moving across it at your own chosen speed. You are made of the rubber. Every particle composing any spacecraft, any crew member, any signal ever transmitted is itself a feature of the same spacetime that enforces the limit. Asking to exceed the speed of light is asking the universe to exceed itself. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, provides the most direct experimental demonstration of this reality available to science. The machine accelerates protons, subatomic particles, with essentially no mass, by everyday standards, around a circular tunnel, 27 kilometers in circumference, using superconducting magnets and electromagnetic fields of extraordinary precision. At full operation, those protons reach 99.9999991% of the speed of light. That final gap, 0.0000009%, is not a small remaining engineering challenge. Closing it would require more energy than the entire LHC experiment consumes in all its years of operation, focused entirely on that single remaining increment of speed. And that increment would still not reach the limit. It would only approach it more closely, while the energy required to close the remaining gap continued to increase without bound. This is not a technical problem that a more powerful accelerator would solve. It is what the mathematics of special relativity predict, confirmed by every experiment ever performed, at every accelerator ever built on every continent, across more than a century of physics research. The limit holds, every time, for everything. Now consider what this means for communication before even addressing travel. A radio signal, electromagnetic radiation traveling at the full speed of light, the fastest any information can move through space, takes 4.24 years to reach Alpha Centauri from Earth. A signal sent today arrives there in the year 2029. Any response to that signal traveling back at the same speed arrives on Earth in 2033. A single exchange of information with the nearest star system requires 8.5 years under the best physically possible conditions. A real-time conversation with Alpha Centauri, the kind of back-and-forth exchange that happens in any ordinary phone call, is not something that requires better technology to achieve. It is something that the structure of space-time makes permanently categorically impossible. The delay is not a lag that faster equipment could reduce. It is a hard physical minimum that no advancement can touch. This matters because it reframes what interstellar contact would actually look like, even in the most optimistic scenario. Detecting a signal from a civilization 1,000 light-years away means receiving information that was sent 1,000 years ago. Sending a reply means the response will arrive there in the year 3025. Whatever prompted the original signal, whatever the civilization wanted to communicate, whatever situation existed when they broadcast that, reality is 1,000 years gone by the time the message lands anywhere. Every science fiction scenario involving real-time communication between star systems, commanders issuing orders to ships across the galaxy, civilizations maintaining ongoing diplomatic relationships across light years, all of it runs directly into this wall, not because of insufficient technology, because of what space-time is. The question that surfaces naturally here, and it is worth sitting with rather than dismissing, is what all of this implies about warp drives, wormholes, and the various faster-than-light mechanisms that populate popular imagination. These concepts appear frequently enough in serious-sounding discussions that many people assume they represent genuine scientific possibilities awaiting only the right breakthrough. The actual status of these ideas in physics is considerably more constrained. And that is a story for later in this account. The deeper question, and the one that does not resolve easily, is whether any civilization, anywhere in the universe, across all of time, has ever looked at this limit, understood it completely, and found not a way around it, but a fundamentally different approach that makes the question of crossing physical space irrelevant. A civilization that accepted the speed of light as absolute might not conclude that interstellar travel is impossible. It might conclude that interstellar travel is simply not the right question. But suppose a civilization decides the journey is worth attempting anyway. Suppose they accept the years, the decades, the centuries of travel time. The next question is not philosophical, it is brutally practical. How much energy does it cost? And the answer is the kind of number that silences even the most optimistic room. But suppose, just suppose, a civilization somewhere is willing to accept the slow journey. How much energy would they have to pay? The answer will silence even the most optimistic. Every civilization that has ever existed operates within a budget. Not a financial budget, something more fundamental, an energy budget. The total amount of power that civilization can generate, store, and direct toward any purpose it chooses. For humanity in 2025, that budget is approximately the combined output of every power plant, every solar panel, every wind turbine, every combustion engine running simultaneously across the entire planet. The question people instinctively ask about interstellar travel is, does a civilization have enough? Do they have a big enough budget to afford the trip? That is the wrong question. The right question is the bill fixed? And the answer delivered without negotiation by the laws of physics is yes. The minimum energy required to move a specific mass to a specific velocity is not determined by the sophistication of the engine doing the work. It is determined by the mass, the velocity, and the speed of light, three quantities that do not adjust based on how advanced the civilization paying the bill happens to be. Physics sets a price, floor, no technology. No matter how far beyond anything currently imaginable can pay less than that floor. The only variable is how efficiently a civilization approaches the minimum, how little energy they waste on heat exhaust and mechanical losses. But the floor itself is non-negotiable. This distinction matters enormously, and a simple example from everyday experience illustrates why. Lifting a car 1 meter off the ground requires a fixed, calculable amount of energy determined entirely by the mass of the car and the strength of Earth's gravity. A hydraulic lift does this efficiently. A team of people with ropes and pulleys does it less efficiently, wasting more energy on friction and mechanical losses. But neither the hydraulic lift nor the rope and pulley system can lift the car for less than the physical minimum. The minimum is set by gravity and mass, not by the sophistication of the lifting mechanism. A civilization 1 million years more advanced than ours could build a lifting device of breathtaking elegance, and it would still require at least that same minimum energy to raise that car 1 meter. Physics does not offer discounts for ingenuity. Now apply this to interstellar propulsion, and the numbers that emerge are the kind that stop conversations. The entire annual electricity consumption of the United States, every kilowatt-hour generated by every power source in the country across a full 12 months, amounts to roughly 4,000 terawatt-hours. That is an enormous quantity of energy by any human standard. It powers hundreds of millions of homes, runs the entire industrial and commercial infrastructure of the world's largest economy, keeps the lights on across a continent. If every joule of that annual energy were redirected not to the economy, not to homes or hospitals or factories, but entirely to accelerating a single city bus to 10% of the speed of light, it would sustain that acceleration for approximately 15 seconds. 15 seconds of thrust toward an interstellar destination. The remaining acceleration needed to actually reach that velocity, the other 99-point-something% of the energy bill, would require thousands of additional years of equivalent total American energy output, all directed at the same single bus with no passengers, no return capability, and a 40-year travel time to the nearest star once it reached speed. That is the cost for a bus, not a generation ship, not a vessel capable of sustaining life across decades of deep space travel, a bus-sized object with no crew and no way home. The reason the numbers are this extreme traces back to a feedback loop built into the physics of every rocket ever designed. Moving a spacecraft requires fuel. Carrying fuel adds mass. Greater mass requires more fuel to accelerate it. More fuel adds more mass. The cycle is self-reinforcing and vicious, and it was mathematically formalized over a century ago in what engineers call the rocket equation. The equation does not care about the sophistication of the engine or the cleverness of the designers. It describes a relationship between mass exhaust velocity and achievable speed that cannot be redesigned away. The Apollo program provides the most visible demonstration of this trap in human history. The Saturn V rocket that carried astronauts toward the moon stood approximately 111 meters tall and weighed close to 3,000 tons at launch. The command module that returned to Earth at the end of the mission weighed roughly 6 tons. The mission consumed nearly 500 times its final mass in propellant just to reach the moon and return, and the moon is, by interstellar standards, essentially in the same room as the launch pad. Scale that trajectory toward another star, and the fuel mass required under conventional rocket physics does not increase proportionally. It increases exponentially. For chemical rockets, the fuel-to-payload ratio needed to reach even 1% of the speed of light exceeds anything that could physically exist. The math does not produce a large number. It produces a number larger than the observable universe has mass to supply. This is not engineering pessimism, it is arithmetic. Antimatter represents the theoretical ceiling of what physics permits in terms of fuel efficiency. When a particle of matter meets its antimatter counterpart, both are annihilated completely, converting 100% of their combined mass into energy. No chemical reaction, no nuclear fission, no fusion process approaches this conversion rate. It is the most energy-dense reaction the laws of physics allow. And across the entire history of human particle physics, every accelerator ever built, every experiment ever run, every country that has invested in high-energy physics research, the total quantity of antimatter produced by humanity amounts to enough to boil a cup of coffee. Not a large pot, a single cup. This is not a funding problem. It is not a technology problem. Producing antimatter requires more energy input than the antimatter itself contains, when annihilated current production methods return roughly 1/1000th of the energy invested. Scaling production to the quantities needed for interstellar propulsion would require energy input so vast that the enterprise becomes self-defeating before it begins. The universe permits antimatter to exist. It does not permit it to be manufactured in useful quantities by any civilization operating within a planetary energy budget. A Type II civilization on the Kardashev scale, one that has achieved the extraordinary feat of capturing the complete energy output of its host star, every watt radiated in every direction, channeled into usable power, would command approximately 400 trillion times the energy budget of Mars, present-day humanity. This is a level of engineering achievement so far beyond current human capability that it belongs in the same category as rearranging continents. And a civilization at that level could, in theory, afford to send a bus-sized probe to the nearest star. One probe, one way, 40 years in transit, no return mission. The most expensive object ever constructed by the most powerful civilization imaginable, dispatched on a 40-year one-way journey to look at a neighboring star system and report back if the communication systems survive long enough to do so. That is what the energy ceiling of known physics actually allows, even for a godlike civilization by human standards. Not a fleet, not an invasion force, not even a crewed vessel with any realistic expectation of return. A probe, one direction. Which raises the question that the invasion narrative of popular culture has never adequately addressed. If even the most advanced civilization physically possible can only afford to send a handful of probes across interstellar distances, where does the imagery of alien fleets arriving at Earth come from? And more pointedly, if a civilization somehow scraped together the resources for a single interstellar mission, why would the destination be a small, rocky planet orbiting an unremarkable star in the outer suburbs of an average galaxy, broadcasting radio signals that have only been detectable for the past century and have barely reached the nearest few hundred star systems? The energy wall does not just make interstellar travel difficult. It makes the specific scenario of alien civilizations arriving at Earth uninvited in force, with the resources to mount any kind of sustained presence, almost physically incoherent when examined against what the laws of thermodynamics actually permit. Set energy aside. Suppose they have enough. Suppose the ship has launched. Suppose the journey has begun. then the thing that will kill that mission is not fuel. It is something no civilization can buy, store, or save time. The year is 1025. A medieval European king sitting in a stone castle somewhere in what is now France or England makes a decision. He is sending an expedition to a distant land, not a voyage of a few months, not even a journey of a few years. He issues a royal decree stating that the descendants of this expedition will reach their destination in the year 11,025, 10,000 years from now. He appoints a commander, loads the ships with supplies, writes down the mission objectives in careful Latin script, and watches the fleet disappear over the horizon. The question is not whether the ships could physically survive that journey. The question is simpler and more devastating. In the year 11,025, would anyone on board still know why they left? Would they still speak a language recognizable to the king who sent them? Would the mission objectives written in that Latin script mean anything to people born 10,000 years after those words were carved? Would the mission even exist as a concept, or would it have been reinterpreted, forgotten, mythologized and replaced so many times across so many generations that the original purpose had dissolved entirely into legend? This is not a hypothetical designed to be colorful. This is the actual social timescale problem that any interstellar generation ship faces. And anthropology, the study of how human cultures actually behave across time, does not offer reassuring answers. No culture on Earth has survived 10,000 years intact, not one. Latin, the administrative language of the most organized empire the Western world has ever produced, is dead. The Roman Empire that spoke it, built roads across 3 continents, and enforced legal codes across millions of people collapsed and left behind ruins. The English language of 500 years ago, the language of Shakespeare, which feels poetic and archaic to modern readers, is sufficiently different from current English that students require dedicated study to read it without confusion. 500 years, that is 5% of 10,000. A ship, isolated in deep space for 10,000 years, would not maintain a culture. It would generate entirely new ones, multiple times over, with each replacement bearing less and less resemblance to whatever the founders intended. When that ship finally arrived at its destination, the people aboard would have no more meaningful connection to the civilization that launched them than a person alive today has to the inhabitants of ancient Mesopotamia. They would share, perhaps, some biological heritage. Everything else, language, values, social structure, purpose, identity, would have been rebuilt from scratch many times over, in a sealed metal container with no external input. The psychological dimension compounds this problem in ways that become visible much sooner than 10,000 years. NASA's simulated Mars mission studies, conducted in isolated habitat environments, and research on personnel stationed at Antarctic bases through polar winters, consistently show the same pattern within less than 12 months of genuine isolation. Group psychology begins to fracture in measurable ways. Social hierarchies reorganize. Small conflicts calcify into lasting divisions. Individuals develop what researchers describe as a psychological compression, a narrowing of mental horizons to match the physical boundaries of the enclosed space. Motivation toward external goals weakens as the environment itself becomes the totality of experienced reality. These effects appear in groups of 8 to 40 people, isolated for months on the surface of Earth, with the knowledge that rescue and return are possible. 10,000 years is not a longer version of 12 months. It is a categorically different social phenomenon operating across hundreds of generations in a closed system with no possibility of external contact or rescue, producing cultural and psychological outcomes that no existing research framework can reliably predict because nothing like it has ever existed. Genetic viability adds another layer of constraint that transforms the romantic image of a brave crew into something considerably more logistically complex. Maintaining sufficient genetic diversity to prevent inbreeding depression across thousands of years of reproduction in a closed population requires, according to current estimates in population genetics, a minimum founding population of somewhere between 5,000 and 10,000 individuals. Some research suggests the number may need to be higher to account for random genetic drift across that many generations. 5,000 to 10,000 people. That is not a crew, that is a small city. With everything, a small city contains political factions competing for resources and governance authority, religious movements arising and fragmenting and producing offshoots, economic inequalities developing between those who control critical systems and those who do not, interpersonal violence, emerging from confinement and social pressure, ideological conflicts about the meaning and purpose of the journey itself. A generation ship carrying the minimum viable human population for genetic survival would be, from its first decade of operation, a fully functioning society, with all the instability and complexity that implies. The most ambitious attempt humanity has ever made to maintain a closed ecological system for human habitation was Biosphere 2, constructed in the Arizona desert and sealed in 1991. 8 people. Approximately 3 acres of enclosed space. Every advantage of being on Earth's surface, normal gravity, the planet's magnetic field, providing radiation protection, abundant sunlight, and the knowledge that the glass walls were the only barrier between the inhabitants and the outside world. That experiment lasted 2 years before oxygen levels dropped to dangerous lows and external intervention became necessary. 8 people, 3 acres, Earth, 2 years. Now, consider 10,000 people in a metal vessel between stars, for 10,000 years with no possibility of external intervention of any kind, ever, until arrival, if arrival ever comes. The generation ship concept addresses the biological problem of lifespan. No individual needs to survive the full journey. But it creates a social problem that biology cannot solve. What happens when the generation born at the midpoint of a 10,000-year voyage, generation 200 or 300 or 500, collectively decides that the mission is a concept invented by ancestors, so distant they might as well be fictional characters? That the destination is an abstraction that holds no emotional reality for people who have lived their entire lives and whose parents and grandparents and great-grandparents lived their entire lives within the same corridors. Compartments. There is no authority that can compel compliance across that kind of temporal distance. The founders are dead. The documents they left behind have been copied, retranslated, reinterpreted, and filtered through hundreds of generations of social change. The mission briefing that made complete sense in the context of the civilization that wrote it may read as incomprehensible, irrelevant, or actively oppressive to people who have never seen a sky. And if that generation decides to turn back, if some political movement aboard the ship accumulates enough support to reverse course and head home, would they even know how? The navigational knowledge required to find Earth from Interstellar distances is not intuitive. It is technical, specialized, and dependent on institutional memory that may have degraded or been lost across centuries of social upheaval. Home for the generation born 3,000 years into the journey is not a place. It is a story, possibly one they no longer believe. But even if the people aboard the ship manage to hold on to their reason and their mission, the physical ship itself does not share that patience. Entropy is not a metaphor. It is not a philosophical observation about the tendency of things to fall apart over time, deployed for poetic effect. It is a physical law, the second law of thermodynamics, describing a real, measurable, universal tendency of energy to disperse and ordered systems to become disordered. It operates continuously at every scale in every environment, without exception, without negotiation, and without any interest whatsoever in the engineering ambitions of any civilization attempting to cross interstellar space. Everything built by any intelligence anywhere in this universe is from the moment of its construction in the process of becoming something else. A cathedral becomes rubble, a computer becomes corroded components, a spacecraft becomes increasingly compromised hardware. The only question is how fast and what interventions can slow the process. No intervention stops it. The most meticulously maintained automobile ever manufactured, serviced on schedule, stored in ideal conditions, treated with every available preservation technique, will not function reliably after 20 or 30 years without replacement. Parts sourced from external suppliers. The rubber in the seals degrades. The metal in the bearings develops microfractures. The insulation on the wiring becomes brittle. These are not failures of craftsmanship. They are the operation of entropy on the materials from which the vehicle is made. The solution for any vehicle on Earth is access to a supply chain, new parts, new fluids, new components, manufactured to specification and delivered when needed. A spacecraft traveling between stars has no supply chain. The nearest replacement parts are depending on how far into the journey the vessel has traveled between 1 and 4 light-years away, and even that nearest source is not a parts depot. it is another empty star system. Every component that fails must either be repaired using materials already aboard, manufactured from raw resources, carried on the ship, or accepted as a permanent loss of capability. And every repair consumes materials. Every manufactured replacement uses feedstock that cannot be replenished. Over time, the inventory of available repair resources can only decrease. Consider the mathematics of reliability over extended timescales. A system with a 99.9% probability of surviving any given year without catastrophic failure, an extraordinarily high reliability rating by any engineering standard, has approximately a 37% chance of surviving 1,000 years intact. After 2,000 years, that probability drops to roughly 14%. After 5,000 years, it approaches zero in any practical sense. A generation ship does not contain one such system. It contains thousands of interdependent systems, each with its own failure probability, each connected to the others in ways that mean one failure can cascade into dependent systems before repairs can be completed. Life support depends on power generation. Power generation depends on structural integrity. Navigation depends on computing systems. Computing systems depend on components that degrade under radiation exposure. Every system is simultaneously failing at its own rate and dependent on systems failing at their own rates. The combined probability that all critical systems remain functional across 10,000 years without external resupply approaches a number that is functionally indistinguishable from zero. Cosmic radiation presents a threat that no shielding solution currently known to physics can fully eliminate. High-energy cosmic rays particles accelerated to near light speed by supernova remnants, neutron star collisions, and active galactic nuclei penetrate virtually any material. They pass through meters of solid lead, through the hulls of spacecraft, through the bodies of crew members, depositing ionizing radiation along their paths, and breaking molecular bonds wherever they travel. In the deep space environment beyond the protective influence of any star's magnetic field, the cosmic ray flux is continuous and intense. Current estimates suggest that astronauts on an interplanetary mission would accumulate radiation doses far exceeding established safety thresholds within a matter of years. The cumulative biological damage across 100 years of exposure, let alone 1,000, represents a serious threat to the long-term health of any biological crew, and a continuous source of damage to electronic systems whose semiconductor components are disrupted at the atomic level by passing high-energy particles. The interstellar medium, the sparse material occupying the space between stars, introduces an additional hazard that scales directly with velocity. At 10% of the speed of light, a particle smaller than a grain of sand carries kinetic energy equivalent to a small conventional explosive when it strikes the hull of a spacecraft. The interstellar medium is not dense by any terrestrial standard, but it is not empty. Dust grains exist in sufficient quantities that a vessel traveling at relativistic fractions of light speed for years or decades will accumulate impacts. Each individual impact damages hull material. The cumulative effect of thousands of such impacts over years of travel is progressive erosion of whatever shielding the vessel carries, the very shielding needed to protect against cosmic radiation, reducing its effectiveness precisely as the duration of exposure increases. No material currently known to science maintains structural and functional integrity across 10,000 years of exposure to this environment. Research into radiation-hardened materials, advanced composites and self-repairing structures continues, and some preliminary results suggest that engineered materials with self-healing properties at the molecular level are theoretically possible. But theoretical possibility and demonstrated performance across millennia are separated by a gap that has not been bridged. What happens when the air recycling system fails at year 3000 of the journey? When the crew aboard have never known any sky other than the interior of the ship? When the technical specialists who designed the original system are 500 generations dead? When the documentation has been copied and retranslated so many times that critical details may have been lost or corrupted? The answer is not a managed repair process with access to spare parts and manufacturer support. The answer is whatever the current generation can improvise from materials that remain, using knowledge that has survived transmission across 3,000 years of social change, applied to a system whose original design they may no longer fully understand. It turns out the greatest challenge is not keeping the ship running. It is something even a perfect ship cannot solve communicating with the people back home. Imagine writing a letter to someone you love. Not an email, a physical letter sealed and sent. Now imagine that the letter takes 500 years to reach its destination, and the reply traveling back at the same speed takes another 500 years to return. By the time the response arrives in your hands, you have been dead for centuries. The person who wrote the reply has been dead for centuries. The handwriting on the envelope belongs to someone whose great-great-grandmother was the one who actually read your original words. That is not a thought experiment designed for dramatic effect. That is an accurate description of what interstellar communication looks like at distances of 500 light-years, which on the scale of the Milky Way is considered relatively close. This is what cosmic correspondence actually looks like. Not a conversation, not even a slow conversation. A sequence of messages dispatched into a void, each one arriving too late to matter, each one composed by someone who will never live to receive a reply, each one referencing a reality that no longer exists by the time it lands anywhere. Consider a specific situation. In 2025, a spacecraft departs Earth on a mission toward a star system, 50 light-years away, traveling at a meaningful fraction of light speed. Engineers back home monitor the telemetry, analyze the data streaming back across the void, and 2 years after departure, they identify something alarming, a critical flaw in the radiation shielding design. A miscalculation in the original specifications means the crew is being exposed to significantly higher doses of ionizing radiation than the mission parameters allowed. The flaw is serious, potentially fatal over the long term. The engineering team works around the clock. They develop a repair protocol, a workaround using materials already aboard the ship, and they transmit the instructions immediately. The signal leaves Earth traveling at light speed, the maximum velocity any information can travel. That signal takes 50 years to reach the ship. When the crew finally receives the warning and the repair instructions, they have been living with the flawed shielding for 50 years. Whatever biological damage the elevated radiation exposure has caused across those 5 decades has already occurred. The repair, even if executed perfectly, addresses the future but cannot touch the past. The people who identified the flaw and composed the warning are 50 years older, most of them are dead. The institutional knowledge that produced the repair protocol belongs to a generation of engineers who were children when the ship launched. And the crew's reply confirming receipt, reporting their condition, describing what the 50 years of exposure has actually done to them, will take another 50 years to reach Earth. A single exchange of critical safety information requires a century. This scenario describes a mission to a star, 50 light-years away. For a mission to a star, 100 light-years distant, double every number. For 1,000 light-years, multiply by 20. The communication lag does not scale as an inconvenience. It scales as a complete severance of any meaningful connection between the vessel and its origin. A ship that departs Earth today toward a star 100 light-years away does not gradually lose contact with home. It becomes an independent civilization at the moment of launch. Every decision made aboard that vessel, every medical emergency, every structural failure, every navigational choice, every social crisis among the population must be resolved entirely from within. There is no mission control to consult. There is no technical support available. There is no authority that can issue updated orders in any time frame that could influence any situation currently unfolding. The ship, and everyone aboard it, are from the instant the engines ignite permanently and completely alone. The implications extend beyond the practical. When a vessel traveling at 10% of light speed finally arrives at its destination after 1,000 years of transit, the civilization that launched it has had 1,000 years to change. The government that authorized the mission dissolved long ago. The scientific institutions that designed the ship have been reorganized, renamed, merged, or abandoned. The specific people who cared about this mission, who championed it, funded it, argued for it against competing priorities, are 40 generations dead. The data the ship transmits upon arrival will travel 1,000 years back to Earth before anyone receives it. When that data arrives, whoever receives it may find that the language in which it was encoded has shifted enough to require translation. The scientific questions the mission was designed to answer may have been rendered obsolete by 1,000 years of independent research on Earth. The star system being reported on may already be known in greater detail from telescope observations conducted in the intervening centuries. The mission's findings, the product of 1,000 years of travel, and the lives of every generation that lived and died aboard the ship may arrive at a civilization that responds with something between mild historical interest, complete indifference. This is not a failure of the mission designers. It is the structure of time operating on civilizational scales. Which raises a question that does not have a comfortable answer. Is any rational civilization capable of genuinely committing resources, not symbolic resources, but the kind of civilizational investment that a multi-thousand-year interstellar mission requires to an endeavor whose results will arrive after the civilization itself may have transformed beyond recognition? Is there a decision-making framework, any framework, that justifies this expenditure when the return on investment is measured in millennia and the investors will be long gone before the first data point comes back? And if the answer is no, if rational civilizations consistently conclude that the math does not justify the investment, then what does that imply about the civilizations that may have existed for billions of years before us, with billions of years in which to ask the same question and reach the same conclusion? The silence we hear from the cosmos may not be the silence of absence. It may be the silence of civilizations that did the calculation. That question about the silence leads to a larger problem, a paradox that scientists call the Fermi paradox, and the answer to it may be more unsettling than anything mentioned so far. Since becoming fully operational in 2022, the James Webb Space Telescope has done something no instrument in human history could do before it directly analyzed the atmospheric chemistry of planets orbiting distant stars. By 2024 and 2025, the telescope had examined the atmospheres of dozens of exoplanets in or near the habitable zones of their host stars, the orbital regions where liquid water could theoretically exist on a planetary surface. The results have been scientifically extraordinary, and for anyone hoping for immediate confirmation of life beyond Earth, quietly sobering. Carbon dioxide detected here, water vapor signatures identified there, methane readings that required careful interpretation to distinguish from geological rather than biological sources. What the telescope has not found across dozens of analyzed worlds is a clear, unambiguous biosignature, a chemical signal that cannot be explained by non-biological processes, and that points definitively toward living systems actively modifying their planetary environment. This does not prove that life is absent from those worlds. The telescope's capabilities, impressive as they are, have limits. Detecting the specific combination of gases that would constitute strong evidence for biology requires observation, time, atmospheric clarity, and favorable orbital geometry that not every target provides. The absence of a confirmed detection is not the same as confirmed absence, but it contributes to a pattern that has been accumulating across decades of increasingly sensitive observation. The universe examined at every scale, and with every instrument available, has not yet offered any unambiguous signal of intelligence beyond Earth. The Milky Way is approximately 13 billion years old. Stars with conditions suitable for rocky planets have been forming for most of that history. If even 1% of those stars host planets in habitable zones, and even 1% of those planets develop intelligent life, the resulting number of potential civilizations across galactic history runs into the millions. Some of those civilizations would have had a head start of billions of years relative to humanity. A civilization that emerged 2 billion years before us, developing technology at even a fraction of our rate, would have had time to transform their star system, their neighboring star systems, and potentially a significant portion of the REIT galaxy in ways that should be detectable across interstellar distance. The universe should, by this reasoning, be loud. It should be structured. It should show signs of engineering at scales that no natural process produces. Instead, it is quiet, uniform, and organized entirely according to physics rather than intention. This is the Fermi paradox, named for physicist Enrico Fermi, who reputedly asked the question at a lunch conversation in 1950 if the conditions for intelligence are common and the universe is old enough for it to have arisen many times. Where is everybody? The standard responses to this paradox form a long list. Civilizations destroy themselves before achieving interstellar capability. Intelligent life is far rarer than the optimistic estimates suggest. Civilizations choose not to communicate. They communicate in ways we cannot detect. They exist, but have not yet reached us. Each of these explanations has problems. Each leaves aspects of the silence unaccounted for. There is one explanation that receives less attention than it deserves, possibly because it is less dramatic than the alternatives. The silence is not a paradox at all. It is the expected result when distance, energy, and time operate simultaneously on every civilization that has ever existed. Every signal ever broadcast by any civilization weakens as it travels. The physics governing this weakening is precise and unforgiving. Intensity drops with the square of distance. A signal that is strong enough to be clearly detectable at 1 light-year becomes 4 times weaker at 2 light-years, 9 times weaker at 3, 100 times weaker at 10. By the time any radio transmission travels thousands of light-years, the energy arriving at any given point has dispersed across such an enormous volume of space that distinguishing it from the natural radio emissions of stars, pulsars, and the cosmic microwave background requires a receiver of a sensitivity that may exceed anything physically constructible. Civilizations are not silent because they choose silence. They are silent because the inverse square law does not negotiate. The entirety of humanity's radio output, every broadcast, every radar pulse, every military transmission, every television signal sent into space since the early 20th century, forms a sphere of detectability, roughly 200 light-years in radius. That sounds substantial until it is placed against the 100,000 light-year diameter of the Milky Way. Humanity has effectively announced its existence to approximately 0.0002% of its own galaxy. The other 99.9998% of the Milky Way has received no signal from Earth that could be meaningfully distinguished from background noise. The first American television broadcasts images transmitted in the 1930s from towers in New York are currently traveling through space at the speed of light. By 2025, those signals have reached stars approximately 90 light-years away. When they arrive after 90 years of travel across the void, the signal strength has diminished to the point where detecting it would require instruments of a sensitivity that does not currently exist and may not be achievable. The very first evidence of human technological civilization racing outward at the maximum speed the universe permits arrives at its destinations as a whisper indistinguishable from the noise of the cosmos. If civilizations within a few hundred light-years of Earth are broadcasting similar signals, the same mathematics applies in reverse. Their transmissions, weakened by distance and dispersed across vast volumes of space, may be arriving at Earth right now too faint to separate from the electromagnetic background that fills the universe at every frequency. The silence may not be empty. It may be full of signals too quiet to hear. This reframes the Fermi paradox entirely. The question is not why the universe is silent despite being full of civilizations. The question is why anyone expected civilizations separated by thousands of light-years to be audible to each other in the first place. The physics of signal propagation ensures that the effective range of any electromagnetic communication is a tiny fraction of galactic scale. Every civilization broadcasts into a bubble. The bubbles rarely overlap, and when they do, the signals arriving at the intersection point are so attenuated that recognition requires instruments that push the boundary of what any given civilization can build. The universe is not withholding information. It is operating according to its own rules, and those rules produce isolation as a natural consequence, not as an exception, not as a temporary condition awaiting a technological solution, but as the default state of any intelligence embedded in a galaxy of this size, governed by physics of this character. But this is where the story turns in a direction few expect, because there is one final argument, one supposed escape route that many believe could overcome all these barriers. And examining it carefully will reveal the most surprising thing in this entire account. There is an argument that surfaces reliably whenever the physical barriers to interstellar travel are laid out in full. It arrives in comment sections, in late-night conversations, in the responses of otherwise careful thinkers who have followed every number and every constraint and still feel that something is being missed. The argument sounds humble. It sounds open-minded. It sounds like the kind of thinking that serious people should embrace. It goes like this: a civilization 1,000,000 years more advanced than us will find a way. We cannot imagine their technology any more than a medieval peasant could imagine a smartphone. Our inability to solve these problems says nothing about whether they are solvable. Advanced enough means anything becomes possible. This argument contains a logical error so fundamental that identifying it changes the entire conversation. The error is a confusion between two completely different categories of limitation: engineering limits and physics limits. These are not the same thing. They do not respond to the same solutions. And conflating them produces conclusions that sound reasonable but are structurally false. Engineering limits are constraints imposed by the current state of materials, manufacturing, computing, and design. They yield to time, investment, and ingenuity. The Wright brothers could not build a jet engine in 1903 because the metallurgy, the thermodynamics knowledge, and the manufacturing precision required did not yet exist. Those were engineering limits. A more advanced civilization, or even the same civilization a few decades later, overcame them. Engineering limits are real walls, with doors that better technology can eventually open. Physics limits are different in kind, not just in degree. They are not constraints imposed by insufficient knowledge or inadequate materials. They are properties of the universe itself, relationships between quantities that do not change based on who is doing the engineering or how long they have been practicing. No civilization at any level of advancement operating anywhere in this universe can build a circle whose circumference equals a straight line. That is not an engineering failure. It is a violation of what the word circle means in a geometry that describes actual space. The constraint is not technological, it is definitional. The speed of light occupies the same category. It is not a barrier that more powerful engines push against and eventually break through. It is a structural feature of the relationship between space and time, the same relationship that governs every particle, every wave, every interaction in the observable universe. The reason nothing with mass can reach or exceed light speed is not that current engines are insufficient. It is that approaching light speed causes the effective energy requirement to approach infinity, not a very large finite number, but actual mathematical infinity. There is no engine powerful enough to supply infinite energy because infinite energy does not exist as a finite quantity available for engineering purposes. The constraint is mathematical, not technological. No civilization, however, ancient or capable, can pay an infinite energy bill. The bill is set by physics, not by the sophistication of the payer. Now take the Kardashev scale, the classification system proposed by Soviet astronomer Nikolai Kardashev in 1964, which ranks civilizations by their total energy consumption. A Type 1 civilization controls the full energy resources of its home planet. A Type 2 harnesses the complete output of its host star. A Type 3 commands the energy of an entire galaxy. These classifications are frequently invoked to suggest that sufficiently advanced civilizations would find interstellar travel trivial. A Type 3 civilization controlling the energy of 400 billion stars, the argument goes, could surely afford to send ships anywhere in that galaxy. The energy wall described earlier would simply dissolve before such staggering capability. Read the Kardashev scale more carefully. A Type 3 civilization harnessing galactic-scale energy still sends every ship it launches into a universe governed by the same equations. The minimum kinetic energy required to accelerate a given mass to a given velocity does not decrease because the civilization paying for it is more advanced. It is determined by mass velocity and the speed of light, three quantities that do not negotiate with Kardashev ratings. A Type 3 civilization can afford to launch more ships than a Type 1. Each ship still costs the same minimum energy per kilogram of mass per unit of velocity. Each ship still travels at sublight speeds. Each ship still takes centuries or millennia to cross the distances between stars. More energy means more missions are possible. It does not mean each mission becomes cheaper, faster, or exempt from the physics it has always operated under. The Kardashev scale describes the size of the checkbook. It says nothing about the price on the menu, and the price is set by physics. Then there are the proposals that claim not to work within physics but to circumvent it entirely. Warp drives, wormholes, faster-than-light travel of various theoretical designs. These concepts appear with such regularity in popular discussions of interstellar travel that many people assume they represent genuine scientific possibilities, temporarily out of reach, but ultimately achievable with sufficient advancement. The actual scientific status of these ideas requires a more direct statement than they usually receive. The Alcubierre warp drive proposed by physicist Miguel Alcubierre in 1994 describes a mechanism in which space itself contracts in front of a vessel and expands behind it, creating a bubble of locally flat spacetime that moves faster than light without the ship inside exceeding light speed relative to its immediate surroundings. The mathematics of this proposal are internally consistent within the framework of general relativity. This is sometimes described as the concept being theoretically possible, a phrase that does a great deal of work while saying very little. What the Alcubierre solution actually requires is exotic matter with negative energy density, a form of matter that gravitationally repels rather than attracts, that weighs less than nothing in a physically meaningful sense. No such material has ever been observed anywhere in the universe. No theoretical framework in physics produces it in quantities relevant to engineering. Early calculations of the energy required to maintain an Alcubierre bubble produced figures exceeding the mass energy of the observable universe. Later refinements using optimized bubble geometries reduced this estimate to something in the range of the mass energy of a planet the size of Jupiter, converted entirely and perfectly into this exotic material that has never been detected using processes that have never been demonstrated to sustain a configuration that has never been produced. Calling this theoretically possible is approximately equivalent to calling division by zero theoretically possible if sufficiently powerful computers are applied to the problem. The mathematics permit the symbol to be written. The physical universe does not permit the operation to be performed. The Alcubierre drive is a mathematical curiosity that lives inside the equations of general relativity and has no demonstrated pathway to physical existence. Wormholes present a parallel situation. Einstein-Rosen bridges theoretical tunnels connecting distant regions of space-time emerge from the mathematics of general relativity as geometric solutions. They exist on paper. Every solution that produces a traversable wormhole, one through which something could actually pass, also requires exotic matter with negative energy density to hold the tunnel open. Without this material, any wormhole that formed would collapse in a time frame measured in Planck units, intervals so brief that they are below the scale at which the concept of passing through has any physical meaning. Additionally, traversable wormholes would allow information to travel faster than light between distant points, which creates causal paradoxes, situations where effects precede their causes that most physicists regard as strong evidence that such configurations cannot physically exist, regardless of what the equations permit on paper. As of 2024 and 2025, no experimental evidence for exotic matter with negative energy density has emerged from any particle physics experiment, any cosmological observation, or any other branch of empirical physics. The proposals that require it remain mathematical possibilities, in the same sense that a geometric construction that violates the axioms of Euclidean geometry is a logical possibility. It can be described, but it cannot be built in the space that actually exists. If the most advanced theoretical physics available cannot identify a physically realizable path around the speed of light, if every proposed mechanism requires either infinite energy or materials that may not exist, then it is worth asking whether the problem itself is being framed correctly. The barriers to interstellar travel are not puzzles awaiting solutions. They are descriptions of what the universe is. And a civilization sufficiently advanced to understand that distinction completely might arrive at a conclusion that is almost never considered. Perhaps the most intelligent response to these barriers is not to attempt overcoming them. Perhaps the most advanced civilizations in the galaxy are not the ones that built the fastest ships. Perhaps they are the ones that recognized clearly and early that faster ships were not the answer and turned their attention elsewhere. This is the perspective that inverts every assumption, and it may be the real answer to the silence of the universe. Reframe the question entirely. For the duration of this entire account, the question has been, why haven't they reached us? Why, given the age of the universe and the statistical likelihood of intelligent life arising across billions of years, has no civilization managed to cross the interstellar distances and make contact with Earth? But there is a prior question that almost never gets asked. Why would they want to? This is not rhetorical deflection. It is a serious challenge to an assumption so embedded in human thinking about alien civilizations that it rarely surfaces as an assumption at all. The assumption that any sufficiently advanced civilization would naturally want to expand outward, explore neighboring star systems, and eventually spread across the galaxy. This assumption feels obvious because it describes human history accurately. Every civilization on Earth that developed sufficient navigation technology did expand outward. The age of exploration, the colonial period, the settlement of continents. All of it followed the same pattern. Capability produces expansion. But every expansion in human history was driven by a specific economic logic. Resources were scarce at home and abundant elsewhere. Land was finite and populations were growing. Trade routes created wealth that justified the enormous risks of ocean crossing. The economic calculation in every case was straightforward. The cost of the journey was less than the value of what could be obtained at the destination. A civilization capable of interstellar travel has by definition achieved energy production and materials processing at a scale that makes the resource economics of expansion fundamentally different. A Type 2 civilization capturing the full output of its star has access to energy quantities that dwarf anything available on any individual planet. A civilization with that energy budget can synthesize any material, sustain any population, and construct any physical environment it chooses within its home system without traveling anywhere. The resources that drove human expansion across Earth, arable land, mineral deposits, fossil fuels, fresh water, are problems that sufficient energy and sufficient technology dissolve entirely. What then is the economic justification for crossing 25 trillion miles to visit the nearest star? What does that neighboring system offer that cannot be obtained or manufactured at home? If the answer is nothing that justifies the cost. And for a sufficiently advanced civilization, the honest answer may well be nothing then. The rational decision is not to go, not because of inability, because of calculation. There is a deeper possibility still, and it involves a transition that human civilization is only beginning to glimpse. The most resource-intensive activities of any civilization, exploration, communication, entertainment, scientific research, social interaction, can increasingly be conducted in digital rather than physical space. A sufficiently advanced civilization might discover that the digital frontier is effectively infinitely cheaper to develop than physical space, and capable of providing experiences indistinguishable from or superior to anything physical reality offers. Why build a generation ship to carry 10,000 people across 4 light-years of void, when the same civilization could create a simulated universe of arbitrary complexity, populated by minds of arbitrary richness at a fraction of the energy cost? The physical universe offers new star systems to visit. The digital universe offers new realities to construct. For a civilization that has mastered both options and must choose where to invest its resources, the mathematics of that choice may not favor the physical frontier. This is sometimes called the simulation hypothesis in popular discourse, but the more grounded version of the idea does not require anything philosophically exotic. It simply notes that as computational power increases, the ratio of experience available per unit of energy in digital space improves continuously, while the ratio of experience available per unit of energy in physical interstellar space remains fixed by physics and never improves. A civilization advanced enough to notice this trend and respond to it rationally might conclude without any loss of intelligence or ambition that the stars are less interesting than what can be built without ever leaving home. Breakthrough. Listen, the most comprehensive search for extraterrestrial intelligence ever conducted has monitored millions of radio frequencies across thousands of star systems since its launch in 2015, with expanded capabilities through 2024 and 2025. The project uses some of the largest radio telescopes on Earth, applies sophisticated signal processing algorithms designed to identify patterns inconsistent with natural sources, and has produced no confirmed detection of artificial signals from beyond our solar system. This result does not prove that no civilizations exist, but it does suggest something about the ones that might. If advanced civilizations were broadcasting, if interstellar communication were a priority for any civilization that had achieved the capability, Breakthrough Listen's sensitivity should be detecting something. The silence is consistent with a universe in which advanced civilizations either cannot communicate across these distances effectively, or have concluded that broadcasting into the void is not worth the energy expenditure, or have turned their attention to forms of activity that produce no detectable electromagnetic signature at interstellar distances. Any of these possibilities points toward the same conclusion. The civilizations that have been around long enough and learned enough to make truly rational decisions about resource allocation may have looked at the cost-benefit analysis of physical interstellar expansion and quietly, without drama, decided against it. There is something almost funny about this, if the word applies. Humanity has spent decades imagining that the mark of a truly advanced civilization is the ability to cross the stars, that the pinnacle of development is a species that has spread across the galaxy and visited thousands of worlds, encountered thousands of other species. But perhaps the actual mark of true advancement is recognizing clearly and without sentimentality that crossing the stars is among the least efficient uses of energy imaginable, and choosing to invest those resources elsewhere. Perhaps the most advanced civilizations in the Milky Way are not the ones that built the fastest ships. Perhaps they are the ones that were smart enough to realize that building fast ships was not the answer. If cosmic silence is the signature of wisdom rather than absence, if the universe is quiet because the civilizations old enough to know better have chosen silence over expansion, then what does that imply about humanity's current enthusiasm for interstellar ambition? Is that enthusiasm the energy of a young species still at the stage where expansion feels like the natural response to capability? Are we, as a civilization, at the developmental equivalent of a teenager who has just gotten a driver's license and cannot imagine why anyone would choose to stay home? And if the civilizations that have been around for billions of years have learned to stay, what did they learn that we have not yet understood? Whatever the reason, physics, energy, time, or choice, the conclusion converges on the same point. And that point is not despair, it is one of the deepest truths the universe has ever revealed to humanity. The silence of the cosmos has been treated throughout this entire account as a problem to be explained, a mystery, a gap between what probability suggests should exist and what observation actually confirms. Civilizations should be out there, the math says so. And yet the universe offers nothing, no signals, no megastructures, no evidence of engineering at scales that would be visible across interstellar distances. The silence feels like an accusation, as though the universe is withholding something that should rightfully be available. Consider the possibility that this framing is exactly backwards. The silence of the universe may not be evidence of emptiness. It may be evidence of abundance, of a cosmos so full of civilizations, each burning brilliantly within its own isolated bubble of space and time, that the silence is not the absence of voices, but the inevitable acoustic consequence of a library in which every reader is separated from every other reader by distances that no sound can cross in any meaningful time frame. Imagine a library, not a building, but something at a different scale entirely. A library the size of a continent, with billions of books arranged on shelves that stretch from horizon to horizon in every direction. Each book is a civilization complete, internally coherent, full of accumulated knowledge, art, memory, grief, discovery, and story. Every book exists simultaneously. At this very moment, in whatever present tense the library occupies, all of them are open. All of them are being written. All of them contain minds, actively engaged in the project of understanding the universe they find themselves in. But each book sits on its own shelf, separated from its nearest neighbors by miles of open floor. No reader can move fast enough to reach another book before the library itself changes, before the books already visited have added new chapters, before the books not yet reached have been partially rewritten by the passage of time. The library is full. It has never been empty. But no single reader can experience more than the smallest fraction of what it contains. Because the library is too large, and the readers move too slowly, and time does not pause to accommodate the journey. This is the universe, not a silent void waiting to be populated, a full library in which every civilization is simultaneously present and permanently unreachable. The physics that enforces this isolation operates at a dimension that is easy to state and nearly impossible to fully absorb. If a civilization exists 1,000 light-years from Earth, a relatively modest distance on the scale of the Milky Way, the light arriving from their star tonight left that star 1,000 years ago. The image of their sun that any telescope on Earth could capture is not an image of where they are now. It is a record of where they were in the year 1025, when Europe was in its medieval period, when the Song dynasty governed China, when no human being on Earth had any conception of what a galaxy was. Whatever that civilization looks like today, whatever they have built, whatever they have discovered, whatever crises they have survived or succumbed to in the intervening millennium, that reality is invisible to Earth. The light carrying that information has not yet arrived. It will not arrive for another 1,000 years. The relationship runs in both directions. Any civilization 1,000 light-years away that points its telescopes toward our sun tonight receives light that left Earth 1,000 years ago. They see our planet as it was in the year 1025. No cities visible from space, no radio emissions, no satellites, no detectable signature of the industrial civilization that has transformed Earth's surface and atmosphere in the centuries since. From their vantage point, Earth may appear to be a quiet, rocky world with an interesting oxygen-rich atmosphere, potentially biological, possibly worth monitoring, but showing no evidence of the technological civilization that has existed here for the past 2.5 centuries and is reading this account right now. Neither civilization is seeing the other as it actually exists in any shared present moment. They are exchanging information across a temporal gulf that makes the concept of now meaningless at interstellar scales. Special relativity formalizes this. There is no universal present that spans interstellar distances. What is simultaneous in one reference frame is sequential in another. The universe does not have a single present moment shared by all observers. Every civilization exists in its own temporal bubble, its observations of other stars, revealing not what those stars are doing, but what they were doing years, centuries, or millennia in the past. This is not a technical limitation awaiting a better telescope. It is a geometric property of a universe in which information travels at a fixed finite speed. No instrument will ever show any civilization what a star 1,000 light-years away looks like right now, because right now, at that distance, is a concept the universe does not support. What this means for any individual human life is something that requires a moment to settle before its full weight becomes apparent. Every person alive on Earth today exists in a specific location in space and time that is in the most literal physical sense, unique and unrepeatable. The particular configuration of matter and energy that constitutes this planet in this solar system. At this moment, this exact intersection of space and time is not accessible to any other observer in the universe. Not because of travel limitations, though those are real, but because the light carrying the image of this moment is only now beginning its journey outward. It will not reach even the nearest star for over 4 years. It will not reach most of the galaxy for tens of thousands of years. It will never reach the edges of the observable universe before the expansion of space carries those regions beyond any possible contact. The present moment on Earth is a secret the universe is currently keeping from everyone else. Not temporarily, permanently, in the sense that by the time the information of this moment reaches any other civilization capable of receiving it, this moment will be history, ancient history by human reckoning, if the receiving civilization is more than a few thousand light-years away. This transforms the experience of being alive on this planet in a way that is difficult to articulate without sliding towards something that feels more like poetry than physics, though the physics is entirely real. Every ordinary moment, a conversation, a meal, a clear night when the stars are visible, is occurring at a coordinate in space-time that no other intelligence in the universe can currently observe, that no other civilization is simultaneously experiencing. That exists in a genuine solitude, not because the universe is empty, but because the universe is structured in a way that makes each inhabited world its own irreducible present. The isolation is not a failure, it is in some sense a kind of protection. Each civilization gets to be fully itself, without interruption or observation, developing in the direction its own nature and circumstances dictate, writing its own story without any external author. The walls of distance and time that prevent contact also prevent interference. If the universe arranged its physical constants differently, if light traveled faster, if space were smaller, if the energy costs of interstellar travel were orders of magnitude lower, civilizations would not be isolated from each other. They would be entangled with each other, influencing each other, competing with each other, perhaps dominating or erasing each other, in the way that technologically superior civilizations on Earth have historically affected less developed ones. The isolation that feels like loss may simultaneously be the condition that allows each civilization to exist as itself, fully and without external disruption, for as long as its own internal dynamics sustain it. Whether the universe designed this outcome in any intentional sense is a question that physics cannot answer. What physics can say is that the constants of this universe, the speed of light, the relationship between mass and energy, the geometry of space-time, produce this result consistently everywhere for every civilization that has ever existed, or ever will exist within this cosmos. The isolation is universal. It is applied without exception, and it is from a certain angle. One of the most profound features of the universe that any civilization has ever been in a position to notice. If a universe full of civilizations, each sealed within its own bubble of space and time, each burning briefly against the vast dark, each unable to reach or be reached by any other, if this is what the cosmos actually looks like from the inside, then the question of what it means to exist here in the bubble in this moment becomes the most important question available. And that brings us to the final question, the one that neither physics nor philosophy can answer completely, but that cannot be ignored. Voyager 1 carries a golden record. It is a 12-inch gold-plated copper disc attached to the outside of the spacecraft, containing 115 images of Earth and its life greetings spoken in 55 human languages, sounds of wind and rain and surf and birds, and the low rumble of a Saturn V rocket, lifting off a launch pad in Florida, and musical selections ranging from an Azerbaijani folk song to Bach to Chuck Berry. The record includes a stylus and instructions for playing it, encoded in a format that the designers hoped any sufficiently intelligent civilization might eventually decode. Voyager 1 has been traveling for nearly 50 years. It is now in interstellar space, the first human-made object to cross the heliopause and enter the medium between stars. It is moving at approximately 38,000 miles per hour, which is by any terrestrial standard extraordinarily fast. By interstellar standards, it is traveling at a speed that makes the word slow feel like an understatement. According to current calculations, Voyager 1 will not approach within even 2 light-years of any known star for approximately 40,000 years. The probability that it will come close enough to any star system for its golden record to be found and retrieved in any foreseeable time frame is, by any honest assessment, negligibly close to zero. The people who designed that record knew this. Carl Sagan, who led the creative team that assembled the golden record's contents, was not naive about interstellar distances or the odds of any civilization intercepting a drift-tumbling spacecraft in the void between stars. The calculations were available to him. He did them. He understood with full scientific clarity that the golden record was almost certainly a message that would never be read. He made it anyway. This is the fact that stays once everything else about interstellar travel has been examined. Not the distances, which are staggering, not the energy requirements, which are prohibitive, not the time barriers which dissolve civilizations, not the entropy which disassembles everything that matter builds. All of that is real, and all of it matters. And none of it is the most interesting thing about the relationship between humanity and the cosmos. The most interesting thing is that a species that fully understood all of these barriers still chose to carve its voice into a disk of gold and send it into the dark. That choice was not ignorance. It was not the product of a civilization that had not done the math. It was something else, something that does not have a clean scientific name, but that every person who has ever looked at a night sky and felt something beyond simple curiosity will recognize immediately. It is the impulse to reach even when reaching is futile, to speak even when no one can hear, to leave a mark in a universe that will eventually erase every mark anything has ever made, and to do it anyway, because the marking itself is the point. The value of exploration examined honestly has never been entirely about arriving. Every major human journey into the unknown, across oceans, into space, into the structure of matter and the behavior of light, has produced its most important discoveries not at the destination, but in the process. The questions that had to be formulated before the journey could begin, the instruments that had to be invented to make observation possible, the failures that revealed constraints no one had previously understood, the unexpected findings that arrived sideways in data that was being collected for entirely different purposes. Every telescope humanity has ever built is, in one sense, an admission of limitation, a device constructed because human eyes cannot see far enough on their own. But in another sense, every telescope is evidence of something that has no equivalent anywhere else in the observable universe, a form of matter that became curious about the space it occupies and built instruments to extend its own perception beyond its biological limits. The universe produced matter, matter in at least one place, and possibly many, became organized in ways complex enough to look back at the universe and wonder what it is. That wondering, not the answer but the act of asking, may be the rarest and most significant thing the cosmos has generated across its 14 billion years of operation. Black holes are more massive, supernovae are more energetic, galaxy clusters are more structurally imposing, but none of them ask what they are. None of them build instruments. None of them send golden records into the dark on the very small chance that someone somewhere might eventually find them. The universe builds walls of distance, energy, and time around every civilization it produces. These walls are real. They are built from the fundamental constants of physics, and they apply without exception to every mind that has ever existed or ever will exist in this cosmos. No amount of ingenuity eliminates them. No level of technological advancement removes the price floor that physics sets on every interstellar journey. The barriers described throughout this account are not temporary conditions awaiting better engineering. They are the architecture of the reality in which every civilization is embedded. But the universe, for all its precision in constructing these walls, did not build a wall around the question. It did not construct a physical barrier, preventing any mind from looking outward and asking whether other minds exist. It did not encode into the laws of physics any prohibition on the act of reaching, of sending signals, building telescopes, launching probes, engraving records, or simply standing under a clear sky and wondering what is out there in the dark, between the stars. A small species on a dusty planet at the edge of an ordinary galaxy in one of 2 trillion galaxies looks up and asks the question anyway. Not because the answer is accessible, not because the distance is surmountable, not because the physics cooperates, but because asking is what a conscious mind does when it finds itself in a universe this large and this strange and this full of things it does not yet understand. That may be the most human thing that has ever happened, and if the universe is as full as the math suggests, the most universal thing as well. If the cosmos is genuinely populated with civilizations asking the same question from within their own isolated bubbles of space and time, each one sealed off from every other by the same walls of distance and energy and entropy, then the loneliness that attaches to the idea of cosmic isolation is real but incomplete. In the deepest sense, no civilization that asks this question is asking it alone. The question is being asked right now by minds that neither we nor they will ever reach. In languages neither of us will ever hear, on worlds neither of us will ever see. We are isolated by physics. We are not isolated by curiosity. And physics, for all its ruthlessness, for all its infinite energy requirements, and its immovable speed limits, and its entropy, and its vast indifferent distances, has never once in the entire history of this universe managed to extinguish the curiosity of a mind that is truly awake. The walls are real. The question survives them anyway.